Good morning. Our team for this project is composed by Juan Diego Plaza Gomez and me, Jason Leonardo González Huertas. And today, we would like to share our development in the control and supervision of a palletizer machine with a PLC and an SCADA system, all of this in the environment of a digital twin that is afterwards deployed to the actuators in the plant that are in our lab. This project has been realized in the Universidad Nacional de Colombia for the first project of the subject SCADA in April 2022, under the tutorship of the master's degree professional Eduardo Barrera Waldron. The requirements of the project are as follows in this video. The palletizer has two feeder conveyors. In the conveyor above, the palletizer is being fed with boxes, and downwards we are feeding with pallets. The first step is to set up the elevator with a pallet and put it into position to receive the boxes. The boxes are being organized in two different configurations, 3x2 and 2x3. Both configurations are possible with the help of an actuator that does the turning in each iteration if necessary. Once the pallet is full, it clamps the boxes and the plate opens, creating a layer. The process repeats with alternating configuration layers until the pallet is complete with 3 layers. Once this is accomplished, the elevator goes down and the filled pallet goes to the end of the down conveyor right to the exit, and the process repeats itself. To start, we are happy to share with you once again the facilities of our university and our workspace with the PLC, engines and pneumatic systems. In the automation lab, we can see a board with the power distribution and our PLC. In the slot 0, we can appreciate the Allen Bradley PLC CPU Compact Logix L30ERM, which has the processor and memory. It stores and executes the program. For the control of an engine with a variable frequency drive, we use the analog output module 1796OE4. In our project, we also use the power source from Allen Bradley. We can see as well the digital input module 1769IQ16, which allows us 14 digital inputs for our sensors. At his side, we have the digital output module 1769OW8 that has 7 outputs with which we can control our actuators. In the board, we can also appreciate the start and stop buttons. They will be one option to start the whole system. In the first place, and related with our above conveyor, we have the engine system, which is confirmed by the magnetic starter that protects the engine from current overloads, the soft starter that protects the engine from damage caused by sudden influxes of power by limiting the inrush current associated with the engine startup, and our 1 horsepower Siemens engine. The second engine that we can appreciate is a motor that is controlled by the variable frequency drive. This represents the pallet of output conveyor. This system starts with the magnetic starter, the variable frequency drive that allows us to control the frequency given to the engine from 0 Hz to 60 Hz. This is possible with the analog output of the PLC from 0 volts to 10 volts. At next, we have our pneumatic system that is brought by a source with a compressor from the lab and put in our control valve source and distributed to 2 valves. The first one, a 3-2 valve with an electric actuation and a return by spring, which will control our simple active cylinder that represents the plate, and our second valve, 5x2, that is only activated via electrical and control the double active cylinder that represents the pushing plate. Another important hardware of our project is the PC or laptop, where we will see the factory I/O. As well, another important part is the cell phone, where thanks to Ignition, we will have the interface of our SCADA. For this project, there are four main environments in use. Using the ISA 95 convention, in the control level we have the physical environment and the simulated environment in factory I/O, where the actuators and sensors are and communicate with the logic. The control level is managed by the PLC of Rockwell Automation that was programmed with Studio 5000. And all the information is gathered in the SCADA level, where all the historical alarms and user interface is displayed. In this project we will use the SCADA to send basic commands to our logic, and the SCADA user interface will be reachable from any computer or even phone inside the network of the PLC.
For this project, we use 4 different softwares. In the family of Alan Bradley Rockwell Automation, we have DRS Links and Studio 5000 for communications and programming of the PLC. For the virtual environment, we use Factory I/O and the scene of the palletizer that is included in the software. To create the SCADA, we use the tools given by Ignition software. This is Ignition in general and Ignition Designer.
The goal of this project is not to show all the logic in the PLC. To give an idea, we share this diagram with a graph set-ish architecture. In yellow, we can see the function of each step, and in green the subroutines that were made to make this happen. The first one is the setup of the elevator, that includes activate the conveyor of pallets and put one pallet in the elevator, and by the time it's loaded, the elevator can go up. And the elevator is set. Now we will build each layer in an alternative way between a 2x3 configuration and a 3x2 configuration. In each layer the boxes need to be clamped and dropped in the pallet once a plate opens. The elevator also gets a little down in order to wait for the next layer. Once the third layer is finished, the elevator can go full down and the full pallet to the exit. This process repeats until stopped. In order to show you how all the network works, we will share 3 videos in parallel, those being the physical laboratory, the PC with the factory I/O, and the SCADA in the cell phone. To begin, we give a start to the system in the SCADA. This can be done from the SCADA or from the physical button with the manual slider activated, as we will show with the stop button. Once in automatic mode, we give a start again. As the boxes fill the first conveyor array as we want, the push gets activated and the double cylinder effect also. This repeats as necessary for every layer. Once the layer is filled, as we said, the plate goes open and the simple cylinder goes up. The elevator goes a little bit down after getting the boxes as we said. In the SCADA, we can see the user interface and the representation of the most important sensors in the field. They go red and green when not sensing and sensing respectively. The next essential possibility in an SCADA system is the historical. In this case, we show the above conveyor and the double cylinder that represents the push. As we can see, it goes from 0 to 1 in a time plot, showing the historic behavior of the binary output. Once the 3 layers are done, the elevator can go full down and the full pallet goes out. In this conveyor we can control the velocity of the output of the pallet with a slider in SCADA that controls the voltage in the output of the PLC to the frequency driver. A last essential use of SCADA is the usage of alarms with historical purpose and with all the information necessary. Ignitions give us the options to filter and to show a defined alarm for a given action. Each alarm is associated with a timestamp and a label, all in a friendly user dynamic table.
As you could see, there is a huge delay in the data transmission. Therefore, it is important to consider the time when the logic is designed. Using a SCADA service is a powerful tool to supervise or automate, but it is important to manage the information in a way that is easy to understand for any user. A good practice when we are designing our logic is to use subroutines to isolate sections which are focused in a determined task in order to facilitate the whole understanding for every person who has to work with it. With all this practice, we see the need for proper standardization in communications, so OPC standards are extremely useful when we are connecting several different softwares and hardwares.